I'm going to develop this from scratch. Essentially, let's close this. We'll start very much from the basics. So what I have done here is I've downloaded the Unitree files from MuJoCo Managery, and then I have here is the template file, which is the one which I've been using to develop code from scratch. Let's call that A1 trot. And then if you run this, it basically simulates just the block, right? We want to change that to the Unitree robot. So it's sitting one level up in this folder. We need the scene file. So I'm going to just go ahead, copy the file name, sorry, the folder name. Then scene.xml. So if I run this now, you'll see that the robot actually falls. Okay, so why is that happening? It's because of if you go to the XML file, let's open the A1 XML. What it's doing when it's set is that it's doing a position control. The position control is right here in the actuator. So it's doing position controls, whatever angles. The key is not in. The key actually puts it in a better position where it actually doesn't fall. So you could actually load this and load the key, which I can do next. Okay, so as I said, we can also load this using the MuJoCo viewer, and that actually might make it easier. So here is the MuJoCo viewer. Let's drop the scene file. Okay, so it falls here too, but then we can fix that. I think we can fix it by doing the load key. Okay, so this is what the position looks like, and those angles are right in this file. If you set this Q pose, which is basically this is the state, and then control, then you can get that. Now we can talk a little bit. I'll talk a little bit more about this. So before we get to the coding, let's just understand the XML and go from there. So the model for the robot is right. Well, this is just this is what I showed you earlier. This is load key. It'll give you this configuration. The zero position is when all the joint angles are zero, and that corresponds to this one. Now, this position is actually cannot be reached on the robot because there are joint limits. And I think if you look at the joint limits, 0, 0 is not one of them. But when you write the kinematics, you need to use this configuration. In fact, you did this for one of the homeworks. It was one of the legs of the robot, and you had to do the kinematics. And this was the zero position, which was used to figure out I think it was the inverse kinematics. Okay, so then we have frames. This is the world frame. So the origin, 0, 0, 0 is here. And then we'll get to how to define the position in just a bit. If you then try to produce the body frames, then you can see there are so many frames. It's kind of confusing. But essentially, if you count these up, you'll count 13. Why 13 is because each leg has 3 degrees of freedom. So there'll be 3 per leg. So 3 times 4 is 12. And then the pelvis, the body in the front, has 1. And that will be the 13th one. So the joints are here. You can see there are these sort of cylinders with a pointed edge. Those are the degrees of freedom corresponding to revolute joints. So each leg would have 3, 1, 2, and 3. You say 1, 2, you can't see it, 3, and then 1, 2, 3, and then same for that one. And you can see this box. This box indicates that it's a slider joint. Okay, so actually it's modeled as a free joint. A free joint has 6 degrees of freedom, positions 3, and orientation 3. However, when MuJoCo writes this down, it actually uses quaternions, because we've seen quaternions is a good way of representing robot configuration. So what we have here is spider joint, sorry, free joint, my bad, free joint. And then this would be revolute. The free joint has, so as I said, there should be 6 numbers describing it, 3 position, 3 orientation. But since it uses quaternions, you really need 7 numbers. So there will be X position, Y position, Z position, and then the quaternion X, quaternion Y, quaternion Z, and quaternion constant. So 7 TOFs. Okay? But the velocity, so that's the position. You also need to figure out the velocity. So the velocity for this is going to be X dot, Y dot, Z dot, omega in body frame, X dot, omega in body frame, Y dot, omega in body frame, Z dot. So there will be 7 DOFs, but 6 velocity variables, right? So for the revolute joint, you only have a single angle. So let's call that theta. And then the velocity would be theta dot. So there would be times, so each leg has 3, and then for 12 degrees of freedom, which is the 4 legs, you'll have this times 12. So when you look at the state, look at Q pose, which is the state, you'll have 7 for free joint, and then you'll have a something like this. You'll have theta 0, theta 1, theta 2. So those would be 1, 2, 3. Sorry, I'll write it 0, 1, 2, right? And then the same thing repeats for the other one. So actually, you know what, I did a mistake. This isn't, it doesn't start from the rear left leg. We can actually check it here. Let's go to this and see where. So the first joint is the first joint is right here, free joint, and that is the name given to that is the trunk. And then what we do is we start off with the front right. So if you can see here, front, FR hip, FR thigh, and then FR cuff. So you start with the front right, and then you go to the front left, and then you go to the rear right, and then rear left. So let me number them as per that. That way it's less confusing. This is not right. So we need to start off from here, front right. This is 0, this is 1, this is 2. So 0, 1, 2. Then we go to the left. So 0, 1, 2. Then we'll go to the rear. 0, 1 will be here, and then 2 is here. Theta 0, theta 1, theta 2. And then finally, let's go to 0, 1, and 2. So theta 0, theta 1, theta 2. So there are 3 per joint, 3, 3, 3, and 3. And then the qvel, the velocity, we'll have 6 for the free, which I wrote down here. These are the 6 ones for the velocity. Then we'll have the theta dot, and so on. So these ones I'll write down here would be, let's choose this. This is the front right, front left, rear right, rear left, and the names here are it's the same thing. So FR is front right, FL is front left, RR is rear right, and RL rear left. Okay, we'll also number them as follows. We'll call this 0, 1, 2, and 3. So when I say leg number, we'll go from 0, 1, 2, 3. It means it's FR, FL, RR, RL. And you'll see that if this has to execute the trot gate, then 1, so 0 will be in unison with 3, and 1 will be in unison with 2. So these will work together. This one and this one will be together. And for the other one, it will be this one and this one together. So this is for the trot gate. Trot gate. 0 and 3 are working together, and 1 and 2 are working together. Yeah, so that's something about how we'll define legs, how we'll define the angles are defined, and so on. So before we get into coding, there's one more thing about dimensions I want to mention, is that we need certain dimensions, and we'll actually not do the recursive Newton-Euler for this. There's a simpler way of doing this, dynamics and control. What we need is basically the kinematics first. So the kinematics, the following things are needed. Which color will stand out? Maybe this one. There's the leg length, which is one parameter. Okay, so the free joint is right here. So there is this dimension, which is width. And then there is this dimension, which let's just call that C. And these can be found from the XML files. Actually, L is, I think, 0.2. W is, I'm blanking on W. We can quickly find that. So if you go to the XML, okay, so take, for example, the RR hip. This indicates the X position, so along the X direction. So 0.183 is C, and then 0.047 is the dimensions along the Y-axis. So 183 and 47. Let me write it on the figure. L is 0.2, W is 0.047, and then C is 0.183. And you'll see that there is a symmetry in the sense that if you start from here, if this is actually negative C, then the one front is positive C, and width goes positive, negative, depending on which leg it is. And so really what you need to do for this, for the kinematics, is really figure out the kinematics of one leg, and then you can just do the same thing for all legs. Provided you take care of C, W, L, and L. So you really don't need to do anything exorbitant here. Nevertheless, I will show you a robot data file which basically plucks everything out. But really, we need kinematics for this case. So